but I thought of presenting the holistic view that how the auscultation sounds. So what auscultation basically means is it's a process of hearing the chest sounds. So often you visit to the doctor, you see that the doctors basically use the stethoscope to hear the chest sound. So this process is basically called the auscultation sound. So we'll be using these sounds to analyze that whether a person is having asthma or he is basically healthy based on these auscultation sounds in conjunction with the deep learning architectures. So this is the presentation layout. So we'll start with the anatomical details of asthma, what happens in case of asthma. Then we'll see that what are the existing diagnostic modality, what basically the doctors in a hospital setting, they basically use to analyze that whether a person is having asthma or not. Then we'll see that what are the difficulty with those clinical modalities. Then we'll basically ask a fundamental question that can we use the lung auscultation sound or the chest sound to diagnose the asthmatic condition. After that, we'll see that what are the major objectives of this particular work and the challenges of pulmonary biosensing. Then we'll see basically we'll be using DL based algorithms. So it's basically a classification problem or identification problem. So anyway, you can think of a supervised learning setup. But we'll see that what are the limitations in case of a supervised setup. So I know that many of you knows this what supervised learning basically means, but for the sake of completeness, I just have taken it into the slide. Then we'll see that how we can leverage the contrastive learning, and later we'll see the data set that we have used, and we'll deep dive into the paper that we have published in INTERSPEECH 2023, that is AsthmaSCELNet. And followed by that, we'll see the results and real-time implementation of the algorithm in embedded processes. So this is the human respiratory system, which basically starts with the nasal cavity. Followed by that, there is a windpipe called trachea. And then trachea basically divides into two parts. These are called the bronchus. Now the bronchus basically even subdivides into smaller airways. These are called bronchioles. And at the end of the bronchioles, you basically have these smaller air sacs or rubber ball-like structure. These are called the alveoli. Over here, what happens is oxygen diffusion process occurs and your deoxygenated blood becomes oxygenated. Now we have to see that how the asthmatic condition basically triggers. So let us consider a person is in a controlled situation, that means healthy. Then his or her bronchus, that means this pathway, will be very much smooth. It is clear, there is no obstruction. However, due to interaction with pollen or allergens, or let's say any sort of bacterial infection, what happens is basically within this lung pathway, hypersensitive reactions basically occurs, and which stimulates the overproduction of this mucus. Then the inner walls of this particular lung pathway. So these are the inner walls of the lung pathway. So this pathway becomes inflamed. At the same time, the tissues surrounding this particular pathway, they becomes stiff and even contract with each other. And therefore, what happens is basically, previously you can see in case of healthy case, there was no obstruction. Now, due to mucus, obstruction due to the contraction of the muscles and the inner wall inflammation, the pathway becomes narrowed down. And what happens is when air will pass through this narrow pathway in a high velocity, then the sound that will be produced, that will be a high frequency sound. So in our research, we are basically trying to use those high frequency sounds to analyze that whether a person is having asthma or not. And these condition also arises these particular symptoms such as shortness of breath, cough, and chest pain. And wheezes are basically the sounds that is basically produced due to this clogging of mucus and narrowing of the pathway. Now, as far as the infection statistics being concerned, so you can see that globally it is around 14% children basically suffers from pediatric asthma, and in India as well, you can see the numbers are quite alarming. So just to compare with a developed country, so for example, India being a middle income country and still a developing country, we can see that the numbers, at least as far as the pediatric asthma is being concerned, it is around 20%, whereas in case of USA, it is around 6.5%. So it is quite alarming as far as Indian context is being concerned. So now, what about the mortality rate? So we can see that globally, this is a report published by WHO. So globally, you can see that around 300 million people basically gets affected and die due to this particular disease. In India also, you can see that number is quite large, and the highest death rate is 22%. Now, as far as city-wise mortality rate is being concerned, so far as the pediatric asthma is being concerned, so you can see that the numbers have been escalated twice or thrice within 5 to 10 years in Pune and Bangalore. So, what are the diagnostic modality that basically the doctors use? So, one gold standard modality is basically the spirometry. So, spirometry, what do you do in case of spirometry? The doctor will ask you to put this particular nozzle into your mouth. Then he or she will clip your nose, and then what he will instruct to take deep breath. And after you take deep breath, when your lung capacity is full, then you have to blast out whatever you have inhaled within 1 second. So the more you try to exhale, the more amount of air that you have exhaled. So that is a good sign. Otherwise, if you are not able to exhale much amount of air within 1 second, that means you have developed some obstruction in the lung pathway. That is an indication of asthma. So if I just show you, there is a video. So this is a very short video, 30-second video. So you can see the process.
And one thing I'm going to do is plug your nose, okay? Just so everything goes through the machine and we don't lose anything. So you put that right in your mouth with your lips nice and tight, your teeth not in the way. So just ordinary breathing, just in and out. Now a big breath. Blow. Blast it out. Keep blowing, 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 and another big breath in. Good. Thank you.
So in the video, we can see that if like a normal candidate, a normal subject can go to hospital and he can perform this experiment very well. There is no issue. However, the problem arises, let's say a person is having acute asthma or chronic asthma. Now, he or she will be first asked to clip his or her nose. Then you have to take deep inspiration. Then you have to do force expiration. So that time, the process becomes quite cumbersome. Often what happens is basically the patients are not able to perform the whole experiment at a single go. They have to go for at least a iteration of 3 to 5 times. So this process becomes quite cumbersome, and patient effort is required and discomfort is also associated with that. The similar kind of test is also there, that is called pheno test, ferric nitric oxide test. There is a machine, so you have to blow into that pipe. The machine will tell you that how much nitric oxide you are basically exhaling along with CO2. In case of asthma, what happens? Due to some allergic reactions, lung basically produces nitric oxide. And there is another technique, peak flow meter, which is similar to this pheno test. Out of these four, nasal bronchoscopy is the kind of a an invasive process. An invasive process means the doctor has to put some probes into the nose. Through nose, first what he will do, he will traverse through the nostrils. It will go to the trachea, and even it can go to the bronchus. That means it can go to the lungs. He will check with camera that whether you have whether any deposition of mucus or sputum has been there. If it is there, then some ventricular measurement will be given to you, and artificially it will be carved out from your throat. So all these processes are quite cumbersome. Patient effort is required and pretty discomfort. So we need some alternative diagnostic modalities such that this patient discomfort issue could be mitigated, and at the same time, the process should be non-invasive, unlike this nasal bronchoscopy. So often you go to a doctor, you see that doctors basically first what they do, they take the stethoscope, they hear your chest, and if he or she sees something noticeable, then he can give you some assistive diagnostic tests to identify whether you have developed any pulmonary disorder or not. So as far as these sounds that we can hear in using stethoscope that is being concerned, so we can see that how these sounds are produced. So when you inhale the air or even exhalation time as well, so the pathway the air basically traverses in a turbulent fashion. So in a typical setting in the lungs, the Reynolds number is basically around greater than 4,000. Uh, so the pathway gets a turbulent heat of the air. And therefore, what happens is basically due to this heating of the air to this particular walls, you get the sounds have been generated. If it is a healthy case, you can see the path is quite dilated. There is no obstruction. So the air flow will be smooth and the sounds will be different than the case of a disease condition. So for example, this is basically a asthmatic case, path is narrowed down. So when air will pass through this particular pathway, it will create a high frequency sound. So that is called wheeze. Similarly, there is another disorder that is called pulmonary edema. What happens in edema is basically in your lungs, you have water deposition. So now you can consider you have water. Now air is hitting to that particular water. So what will happen? It will create some bubbling sounds. So these bubbling sounds are named as crackle. So here I have given a classification of the sounds, and the sounds basically corresponds to which particular disorder. So over here, wheeze is basically correspond to asthmatic disorder. So just to quite illustrate the sound-based classification problem, so I thought of sharing the sounds as well. So you just can hear the sound. So over here, this is the healthy case. So we have acquired the lung sound signals. So just you can hear the sound. So over here, what you have seen is basically like you are inhaling, then exhaling. Then some breath hold is there. Inhalation, exhalation, likewise inhalation, exhalation. So this is a it's in a healthy condition. The airflow is quite smooth and the sound is that you can expect from the air path. Now, what happens in case of asthma, you will see when I will start playing this particular recording, you will see that some gasping as well as some high frequency sound nature will also be reflected. So over here, uh, you'll be able to see one high frequency event. So similarly, here also. So this basically shows a difference in the sound signal itself. So in case of healthy, the frequency response is quite smeared around the lower frequency region. However, in case of asthma, as you have heard that the sounds are quite high frequency in nature. So our main target is basically using these particular sounds to analyze that whether a person is having asthma or not. So the data set that we'll be focusing on, or that we have used to construct the methodology. So that is basically the chest wall lung sound data set. This is a very recently published data set. It came around in 2022. So the data set, what it basically comprises, it comprises the lung sound signal, which is basically acquired using the market available Littmann 3200 stethoscope, which has a sampling rate of 4,000 hertz. And the length of the recordings are quite uneven. They are not fixed. So they are varying from 10 seconds to 50 seconds. And there are several disease classes are there. For example, asthma, pneumonia, COPD. But however, for this particular work, we have considered the asthmatic cases as well as the healthy cases. And from where the sounds have been acquired, so these are the positions. So this is the anterior side of the body and the posterior side of the body. So these acquisition points have been considered to acquire the sound. Now, just to visualize that how the sounds look like. So in the previous case, when I just showed you the sounds, when I just played the audio of that sound, so over there, it was quite, from the time domain signal, it was quite visible that you can see the inhalation, exhalation in case of normal sound signal. You can see there is some structural change in the signal itself, in the time series itself. So in case of asthmatic signal. However, what happens is these are pretty much textbook scenario. So you'll see that I have taken the sounds from this particular repository. So this is pretty much a textbook scenario. The doctor or the subject who is basically under consideration, he's being told that you first take a deep inspiration, then you take a deep expiration. So similarly, over here also in case of asthmatic patients. But in the data set, if you explore the data set, you'll see that the time series barely you can differentiate that just by using a naked eye. We cannot just say that this signal is quite different from this particular signal. So how can we use some alternative technique to analyze this sound to get a better classification accuracy? Because what happens is basically if you just use this time domain, this time series signal, and you pass it through any RNN network or any let's say transformer or something, we found that they are not able to perform pretty well because there is no discriminatory feature feature can be found from these particular direct time signals itself. So what we had used is basically for audio signal, you'll find that the signals are non-stationary. That means the frequency basically changes with time. So that is to capture that particular information, we need to see frequency and time simultaneously. So for that, we have used these melspectrograms. So melspectrogram give you the resolution, like in the y-axis, you will get the frequency content, and in the x-axis, you will get the time content. So over here, you can see that in most of the normal cases, the energy, the red color means that there's a high energy deposition. So the high energy is basically residing in the lower frequency region. However, in case of asthmatic signal, you see that there are several perturbations are there in case of high frequency regions as well. Because you can see this red color basically means that high frequency energy, that means high energy is deposited in the high frequency regions as well, which is not there in case of healthy signal. So in our task, do not process these time domain signals of the time series signals directly to the deep learning architecture. Rather, we extract the Mel spectrogram representation and subsequently we feed it to the model. So one naive objective could be anyway that we'll be using the lung sound signal, we'll be developing some deep learning architecture, and we'll see that how the classification accuracy basically gets affected if we use the Mel spectrogram representation of the lung sound signal. So that is a very naive statement. But as far as the biomedical, if you see any sort of biomedical applications, our main aim is basically just not to do deep learning and get the classification accuracy right paper, etc. We also try to construct the overall standalone system or a point of care system. So what do I mean by point of care system? There will be a on device system on top where you'll be acquiring the data. Then you will feed that data to the embedded processor. Within the embedded processor, whatever algorithm you have developed, that will be deployed and it will do the certain calculations, whatever it is there in the algorithm. And then it will show the classification results, and the result should also be shareable with the doctor. So we are in the era of mobile health. So similarly, so this is a mobile pulmonary biosensing node. So this is the overall structure of this pulmonary biosensing. So let's say a patient is in the in-home monitoring condition. So if he or she is having any sort of asthmatic attack, so there will be a stethoscope. So that stethoscope will acquire the sound through Bluetooth or Wi-Fi that will be shared to the digital assistant, which is basically which could be in the form of any app or something, which will basically take the data. It will analyze the data and show that whether he or she is having any sort of asthmatic attack or not. If asthmatic attack is triggered by this particular mobile app, then what will happen? It will share that particular data as well as the diagnosis report to the server. And through server, the doctor can also check that whether the person is having any sort of difficulty or not. Same as in case of ambulatory situations as well. You can see that in many advanced hospitals, in the ambulance also, they have on-go ICU ambulances. So over there, you'll see these sort of setups are also be installed in the ambulance itself. And you can also store these sort of data into a separate cloud database, which you can also further explore for future research. So what are the main key components that to be considered. One is basically your analog front end, where from where you will be acquiring the data. So we need an acquisition circuit. So that means we need to create a digital stethoscope by our own, which will acquire the sound. So there we need an efficient acquisition. So that means the bit depth, the bit resolution should be very good. The latency would be very less. Power consumption will be very less. Then the algorithm development, obviously, whatever data we have acquired from using that, we need to develop some algorithms. And those algorithms should be deployed into microprocessor or controllers. So therefore, the microprocessor and controller, they do not have very good paradigm of computation units. So therefore, the algorithm should be lightweight. So this is one major aspect of our research as well. So you'll see that the title of the paper is also ventures the lightweight paradigm of neural network. And at the same time, when the wireless module will be there, through which you will be basically transmitting the data into the server. So there also you need some battery management issues are there that should also be taken care of. So the main crux of this particular biosensing node is basically the whatever algorithm or DL algorithm that will be constructing, that should be lightweight. The power consumption on the hardware, that should be as minimum as possible, and the efficient battery management should also be considered. So obviously we'll be using the DL based architectures to classify or to identify whether a person is having asthmatic condition or not. So you can consider that we have the sound signals and we have the labels as well. So over here you can consider the data paired as X, which is basically the sound signal, and Y is basically the corresponding label. So you can think of that, why can't we basically train a supervised model, vanilla supervised model? So over there, what you have to do is basically you, let's say, I have taken the images of cat and dog for illustration. So you feed the dog images of cat and dog, the CNN model. The CNN model will from the CNN model will basically extract some feature representation, and then subsequently this feature representation will be passed through the series of dense layer of the linear layers, and at the output side you will basically check that whether your prediction is correct. If it's correct, then you have not incurred any loss. If your prediction is not correct, then you have to calculate the loss, and that loss has to be back propagated to both these linear layers and the CNN layers. Now, what you basically do by backpropagating the losses? So by backpropagating, you basically update the weights of this particular blocks such that your weight will be modified, and by modifying those weights, you are trying to extract good representational features which can be easily classifiable in the linear layer. So that means you try to, what your aim is basically over here in case of supervised learning is you try to match the label. If label is not matched, you try to update the weights, you try to extract good features, and then subsequently pass it to the linear layers. However, why can't we think of a situation that instead of directly doing this label matching, and by label matching, by incurring the label matching process, indirectly we are trying to learn the good features. Why can't we put supervision on the feature extraction part only? If my feature extraction part is good enough, then what will happen is basically, let's say over here you start with a epoch 0. In epoch 0, the representational feature, high dimensional feature, I have reduced into 2-dimension using t-SNE. So you can see that initially at epoch 0, all the signals or all the classes are randomly scattered. Now, as you go along the epochs, what happens is basically, let's say it is at epoch 200. What happens is basically you try your classification accuracy will be going up, which basically mean that subsequently by learning through those epochs, you are able to extract good features. And what basically good feature basically indicates, that means at the embedding space, they should create class specific clusters. However, in case of supervised learning, you cannot guarantee that these clusters will be sort of the intra-class variability. That means this within class variability should be very compact. So that means within class, the cluster should be very compact, and the intra-class. So let's say you have two clusters like cluster 1 and cluster 2. So the distance between these two clusters should be as high as possible. That means inter-class variability should be as high as possible. But in case of supervised learning, you cannot guarantee that, as because your main aim is to match the labels. You are not interested in putting supervision on the feature extraction part. So here is another example. So over here you see, you start with epoch 0. Through epochs you are learning something, and you can see that you are getting class specific clusters. However, they are not like very sparse in nature. That means they are not quite distant. Like these are two different classes, this brown one and this gray one. They have some sort of mix up is also there. So over here also you can see mix up is also there. But what we want, if like there are two clusters and they are very much distant with each other. So if my features are very well extracted, so I can use any shallow classifier to get it classified with the highest amount of accuracy. So in contrastive learning, we try to explore the supervision on feature extraction part. So over here, this is a naive block diagram of contrastive learning. So what basically do is our first aim is to extract good features. That means this representational feature over here, we put thrust on. So over there, we employ some contrastive loss function such that our feature extraction process becomes very much fine, so that the features will be quite sparse enough, they will be quite distant enough. And then what we can do after we train this CNN block using contrastive loss, we can transfer those weight as a frozen weight. Otherwise, we can fine tune the model again, and then we can subsequently feed those features into a shallow neural network, which is basically G of phi. And then we can get the classification using any sort of, it is a binary classification, it will be binary cross entropy, otherwise it will be categorical cross entropy. So there are two tasks. One is basically the upstream contrastive representation learning task. Another one is basically the downstream classification task. So here also the contrastive learning can be done in a two setup. One could be a supervised setup, one could be an unsupervised setup. So just to give you an overview. So in case of supervised setup, what we want to do is basically, so main aim is the data coming from same class, they should have similar type of representation. Data coming from different class, they should have different sort of representation. That means if this is the f theta of x cat is basically the embedding representation. So this f theta of x cat 1 and cat 2, distance between these two should be as minimum as possible. However, distance between cat and dog embedding should be as high as possible. So what it will do, within class, the variability should be very less. They will be so compact, and that means inter-class, the variability would be too high, such that the clusters will become distant apart. So this is a naive representation of contrastive loss. So we need to minimize the distance between the cat class images or the cat class representations, and we need to maximize the inter-class distances. So this is the this is when you have the labels. So you know that these two images are coming from cat class, these images coming from dog class. Now what happens if you don't have any labels in your data set? So over there, this is the unsupervised setup. But what you do, you create your own supervision. So this unsupervised setup is often called the self-supervised mechanism. So over there, what you do, you take the image, you do a random crop or any sort of data augmentation you do, and you consider that for this particular image, if I take any augmentation of out of this particular image, so the embedding that will be generated from this image and the augmented image, they should be quite alike. They should be quite alike. However, all other data in the batch, their embedding representation will be quite different from the original image. So in this way, you can put your own supervision mechanism and then you can train the model. So this unsupervised setup is often called the self-supervised setup, because you are putting your own supervision there. Here, there is another issue sometimes that you can come across. So let's say you are doing dog class classification. So in the dog class classification, there could be different sort of dogs. So let's say this is a golden retriever. let's say you have another husky. So the husky image, as because you do not know that that particular husky basically belongs to dog class. So what will happen? You will consider that even though that is a dog, you will consider that the embedding should be as distant as possible, because that particular husky image is not the augmented set of the original image. So this is a sort of a drawback of the self-supervised or the unsupervised case of contrastive learning. So to mitigate that, the supervised contrastive learning basically came. So we'll be leveraging the supervised contrastive learning in our framework. And at the same time, there are several contrastive laws. So over here, I have written this L contrast. You find in literature, there are several contrastive laws. So in our paper, we have used the triplet loss function. So in case of triplet loss function, what you do, you have a batch, you have a data, you have the data, you construct the batch. Within batch, you have a pool of data, and in each iteration, what you will do is basically, instead of taking a single data, you will sample three data simultaneously. So one could be anchor data or the reference data, one could be the positive data, and one is the negative data. So the property of positive and anchor is basically they should come from the same class, yi. And anchor and negative has the property that the negative data will come from any other class uh, which is not same as the anchor. So that is why I have written X negative belongs to Yj and I is not equal to J. So that will ensure that their class identity is not the same. Okay, so then what we can do is basically we can pass these images through the neural network block. So this is basically f theta of x. So over here, I have marked this with a double-sided arrow. So what this basically means? This basically means that you are using a single neural network. It seems like there are three neural networks, but effectively you are using a single neural network. And these models are basically identical to each other. That means parameter shared model. These are often called the Siamese neural network. So you pass these images through this parameter shared Siamese neural network and you produce this embedding. So positive embedding, anchor embedding, and negative embedding. So our main aim is basically we'll calculate the distance between anchor and positive, we'll calculate distance between anchor and negative. So intuitively, it should be like, and the distance between these two should be very less, and distance between these two should be very high. So that means if I just say in terms of the mathematical representation, so forget about this gamma first. So what we want is the distance between anchor embedding should be very much less than distance between anchor and negative embedding. But is it so that we just want that the positive and the anchor positive distance should be as minimum as possible and anchor negative distance should be as high as possible? So to mitigate that, the triplet loss paper, so they actually introduced a margin factor or a confidence factor. So they introduced a gamma factor over there. So what basically it means that even if you add gamma with the anchor positive distance as well, the anchor negative distance is still higher. So that means with gamma interval also, if you cross the threshold of the margin, even though the summation of these two anchor distance and gamma, it will be still be less than anchor and negative, which will even further ensure that that the distance between these two are they are quite distant apart. So this is the final loss function. So in the loss function, you can see it is constructed as maximum of 0, comma, this gamma plus anchor positive distance and negated with distance between anchor negative distance. So just a dry run, if I just show you. So let's say our main aim is basically, let's say over here. Let's say we can start from this particular case. So you can see that DAP is larger than DAN. So over there, if you just add gamma with this particular length, so obviously this will get a high value than this one. So it will be maximum 0, comma, something a positive value you will get. That means you are incurring some loss. So therefore, you need to modify this whole weights of this Siamese neural network such that you get a situation like this. over here, you can see that if you add gamma plus this particular distance, it will be still less than this particular distance. So over there, this value is less than this one. So it will be max 0, comma some negative value. So at that condition, the loss will be equal to 0. That means you are not incurring any loss. So over there, you can stop the learning process. So this is a small demo. Like if you start with this particular situation using triplet plus, what will happen is basically now you can see that you are getting very compact class specific cluster. So at the very end, you will get something like this. And this is what to be expected for. If you get some sort of feature representation like this, then your ML classifiers or very shallow classifiers will do a good classification. So now let us talk about the paper. So the paper basically named as AsthmaSCELNet, which basically stands for Asthma Supervised Contrastive Embedding Learning Network. So as we already have talked about that, we'll take the raw lung sound signal, followed by that we'll pre-process the signal. As the lung sound signals are not of uniform length, they are varying from 10 second to let's say 50 second. So we thought of processing the signals in a uniform window manner. So over there, we have considered a window of 5 seconds. So we'll process the 5-second window. So we'll create the chunks of 5-second window with 50% overlap with the next window. So after that, what we do is basically in any biomedical signals, you'll see that when you acquire the signal due to the chest movement, what happens is basically you are breathing in and breathing out. So therefore, what happens, you have diaphragm. So you have lungs and after just below lungs, you have diaphragm. So the diaphragm will expand and contract. And that you can also observe as well if you just carefully see that when you when you do the breathing in operation, your chest expands, and when you breathe out, the chest basically contracts. So this basically creates a very low frequency sinusoidal baseline noise. So we have removed those baseline noise using DFT based filtering mechanism. So it's a filtering mechanism. And after that, we have normalized the signal using min-max normalization. So after doing the pre-processing part, we have extracted the time frequency representation, that is the melspectrogram. And as we have already talked about, within a batch, what we'll do a random sampling and we'll extract the triplet pairs. So this is the positive anchor and negative pairs. And subsequently, these will be passed through this particular lead module. So what basically lead module stands for, which is lightweight embedding extraction backbone. So we over here we have ventured the lightweight neural network architecture such that we can deploy this architecture subsequently in the embedded processes. So these are also the parameter shared Siamese neural network, and this sign basically means that we are training the model. So you get the embeddings and you do the triplet loss based training such that you minimize the distance between these two and maximize the distance between these two. After you train this model, what we have done is basically we have taken the frozen model. Now we don't need these triplet pairs. Now in the training set, whatever data you have, you just feed the data to this particular frozen lead module, and then you can get the embedding representation. And the embedding size is 40x1. And then you can pass it through a very shallow neural network. This is basically a 2-layered MLPNN architecture. And at the end, you have the classification layer, and which is basically activated with sigma to classify whether the data belongs to healthy class or asthmatic class. Now we have to see that what basically the lead module basically constructed with. So in case of lead module, this is a pretty simple CNN based architecture, nothing fancy. So over there you have the convolutional blocks and the ReLU max pooling blocks. Thereafter, we have used the depth-wise separable convolution. So depth-wise separable convolution basically comprises with two stages. One is depth-wise convolution, and then you have point-wise convolution. So this convolution technique, rather than using the standard convolution over here, this basically reduces the computational complexity as well as the trainable parameter numbers. After that, we have used this MS-RIM block. So this MS-RIM block basically means stands for multi-scale residual inception mobile block. And then we have stacked two modules of this one. And then we have used the global average pooling to get the one-dimensional representation along the channels of the output tensor of last MS-RIM block. And then we have used the dense layer with 40 neurons such that we get the embedding dimension with 40 plus 1. Now we need to see that what is the architecture of the MS stream block. So MS stream basically, so this I basically means the inception. So we know that in case of Google Net or Inception Net, they basically uh, taken a new set of NIN structure, network in network structure. So that was named as Inception block. So in Inception block, it basically comprised different sort of kernel based feature extraction process, multi-scale feature extraction process. So over there, most of the process was basically based on the standard convolutional architecture. So over here, what we have used, basically, we have used the either pointwise convolution or the depthwise convolution. So this depthwise and pointwise convolution is basically used to reduce the number of parameters within the inception block. And we have shown in the paper, you'll see that we have reduced around the weights around 16 times than a normal vanilla inception block that was there in case of Google Net architecture. And at the same time, if you see the Google Net or Inception Net architecture, they had 20 such inception blocks. And then after certain inception block, they had something called auxiliary classifier. So those auxiliary classifier used to inject gradient to the model in the backpropagation scene. So instead of doing that, what we have used basically, we have connected a residual skip connection such that while doing the backpropagation, the gradient can get an alternative pathway to flow back to the previous loop. So which basically mitigates the overfitting issue. So this is the overall architecture, and as well as we have already talked about that we want something lightweight. So if you just check the paper as well, so there is full details are there. So the total number of parameter of this particular leap module is around 18,000 something. So this is pretty lightweight as the number of parameters is very less. So now as far as the results are being concerned, so our main target was initially to show that by using supervised setup based training, the training performance was not that good. So we had used the same, so we had used leap plus this MLP in two scenarios. One is basically the vanilla supervised so vanilla supervised learning, where our main aim is basically to do the label matching. And the second one is basically the contrastive learning based training. So over here, in case of normal supervised training, you can see that we have run the epochs for 400 epochs. So over here, you can see that you get some sort of overfitting in the validation set. Over here also, in the training and loss, both in loss and accuracy, both you can see the overfitting is occurring. However, in case of SCL based framework, that is the supervised contrastive learning based framework, you can see that the model is basically converged very quickly within 100 epochs, and you can see that there is no overfitting, and subsequently you can see the accuracy is also pretty impressive rather than this one. So over here we achieved around accuracy of 87%, 88%. Over here we had achieved around accuracy value of 98% or something. Now, why this sort of response we are getting in the case of SCL framework or the contrastive learning framework? So that answer basically is reflected over here. So this is the raw lung sound from both the classes. We have taken basic features from the time domain signal. So initially also we told that if we just use time domain signal directly to use into any RNN architecture or any sort of machine learning classifiers, so it will not be able to classify well as because there is no certain discriminative patterns out there. So the same you can see that initially if you take the raw long sound signal and you just reduce the dimension to 2 dimension using t-SNE, so you get the feature space quite abruptly they are scattered in the 2 dimensional feature space. However, in case of SCL framework, as because our main aim is basically to create good clusters, you can see by using the lead module only, we are getting very good cluster representation after training using the triplet loss based contrastive training. So over here, you can see that asthmatic in the asthmatic case, the within class variance is very less. So that is why it is very compact. And the interclass variability is pretty high. So that is why you can see that they are quite distant apart. However, in case of simple supervised learning, you can see that the embeddings are quite mixed up over here. So in this particular region, you can see that there are a lot of confusion that is happening, and that is why, as the embeddings are not good enough, so how can the linear layers or the simple dense layer will be able to classify them well? So that is why you are getting the same sort of representation in the training and validation accuracy and loss curves as well in case of simple supervised learning. And if we just do the quantitative analysis on both the cases, so you can see that in case of HCL framework, we are getting very high performance. So these are the performance that we use basically in case of any classification techniques. These are pretty naive accuracy measures like accuracy, sensitivity, precision, recall. So in both the case, in all the cases, we can see that HCL basically outperforms the vanilla supervised framework. And over here, we have used the GradCam representation to identify that we had shown you that the raw lung sound signal for the healthy class, they have higher energy deposition in the low frequency region. Unlike in case of asthma, due to wheezing conditions, these are high frequency sounds, the energy is deposited in the high frequency regions. So we tried to see that whether the model is able to capture those informations or not. So over here we have shown that when we do the GradCam from the outermost convolution layer of the lead module. So over here you can see that most of the energy that basically the lead module sees, it is also restricted in the lower frequency region uh, as the healthy case basically concerned. And in case of asthmatic case, you can see that it tries to capture this sort of wheezing representation. So these are the high frequency representation. It tries to capture this wheezing representation at both the sides. Over here also, you can see that some high frequency events are also there. So this basically ensures that model is able to capture the hidden information that is there in the time series and under the underlying in the time series of the healthy and asthmatic lung sound cases. So uh, we published this paper in 2023, and we were the first group who basically used lung sound signal in conjunction with deep learning architectures. So as the supervised contrastive learning is also concerned. So previously, what people had explored is basically other battle, they have used speech-based modality. So speech has also correlation with the lung capacity. You can think of like if you are running for let's say 10 to 15 minutes, then if you're asked to say a full sentence, a long sentence, you'll not be able to do that because your lung capacity is basically affected due to your exercise. So same thing happens in case of asthma. Due to the pathway obstruction, your lung capacity gets reduced and you are not able to speak a single sentence completely. A long sentence you cannot utter continuously. So that is why they tried to explore the modality of speech, and they extracted MFCC based features, and they had used SVL. So the accuracy was not quite significant. Later, Tripathi et al. Used the lung sound signals from the same data set. However, as we have already discussed, the ML classifiers, simple ML classifiers using the time domain features, they were not able to achieve a good accuracy over there. But in conjunction with the deep learning architectures and the melspectrogram representation, we can see that we are outperforming the existing results on asthma classification. Now, the last concern is basically we need to create a prototype out of it. So we should create we have to create a final digital stethoscope by our own, which will be able to capture the sound at good resolution. Then it will be able to communicate with the processor. So over here we have used Raspberry Pi 3 processor, and it will also be able to communicate with the mobile. So we have an Android app also developed over here, and the lung sound quality should be also good enough. So to do that, what we did is basically we brought a very simple stethoscope, market available stethoscope. This was costed around 200 rupees or something. So then we have cut it at the earpiece part. So at the earpiece part, we have cut it down. Then we have inserted condenser microphone over there, and we have constructed our own data acquisition circuitry. So that is the DAC module, which basically comprises different sort of filter mechanism, DC bias amplifier, then bias shifting mechanisms, and after that, these all techniques were done on the analog front end. However, if we try to communicate with the Raspberry Pi or Android system, we need to convert the analog signal to the digital one. So we have used an A to D converter MCP3008, which is a 10-bit, which has 10-bit bit resolution. And at a sampling rate of 8,000 hertz, we have actually we have actually converted the analog signal to digital signal. And subsequently, we communicated with the Raspberry Pi microcontroller using SPI protocol. And after that, the AsthmaSCELNet program has been deployed into this particular microcontroller, and it will. And we have also developed a GUI with the Raspberry Pi microcontroller itself. So over there, you have an option that whether you want to acquire the data from this position or this position, you have to first select that. Then there is a run button is there. So it will collect the data for 10 seconds, and then it will process it with the classification algorithm, and then the diagnosis report will be shown on the display itself. After you see any sort of asthmatic trigger is there, what it will do, it will store the sound signal that is basically captured with this particular DAC module in WAV format or MP3 format. There is it is also connected with the server, and then what it will do, it will mail the recording to the doctor such that the doctor can see the diagnosis report, as well as he or she can analyze the sound that we have captured. So such that it is also a double check that if the sound also refers to some wheezing activity, that means it's a asthmatic condition. And the overall power consumption, we have measured the power using this sort of USB based USB sticks. So this basically measures the voltage and current through the whole process of data acquisition, converting into A to D conversion, and then followed by that the classification that is being done on the microprocessor. So we saw that the peak consumption is basically the average consumption is basically 5.63 watts, and we have a standard deviation of 1.63 watts. So the maximum power that Raspberry Pi can basically take is basically around 16 to 17 watts. So we can see that we are getting around 6 watt power usage over here in case of this particular digital stethoscope is being considered. And this is a real-time implementation demo. So we can see this is the setup. So this is the GUI as well. So what we do is we take, so over here, what we are doing, we are taking the chest piece. We are placing the chest piece on the chest. Then there is a run button. We have press the run button, and it will acquire the data for 10 seconds. Then after, what will happen? It will show you the signal. So over here, you can see that the signal is being shown. Then it will process the signal. It will show the results on the screen. So subsequently, you'll be able to see the results. So over here, now you can see that the results are being shown. So if any sort of, so this is a healthy condition. So the results are healthy, even though you are not be able to see the screen properly. So this is a healthy condition. If any asthmatic condition is basically prevailed, so what it basically does is it sends the information, it transmits this information to the doctor via mail. So this is the real implementation of this particular model, and this is what we have patented for as well. So this is at a TRL3 level condition, and we are now trying to go for a pure ASIC based implementation, such that everything can be miniaturized into very small chip, and it will look aesthetic as well. Because currently the system is quite bulky. It is not like a market available stethoscope that we can see in case of commercialized market available stethoscopes. And these are the references that we have used to create this particular presentation. And I want to thank the collaborator. So Dr. S. Karmakar, he is a professor from AIMS Patna. So he has basically helped us in analyzing the sounds, how to acquire the sounds, and how to basically take decisions based on the sounds. And IIT Patna, AIMS Patna, IC IIT Patna, they have also provided some fund to construct the particular real-time implementation and the digital stethoscope. And thank you for listening. So if you have any question, you can ask.
Thank you, Orko. So if there are any questions, people can ask.
Sorry, can I ask a question?
Yeah,
Yes,
sure.
yes,
Go
yes.
ahead.
Oh, yeah. Okay, yeah. So, so you compared your method with the supervised learning algorithm, with like which is
Yeah.
the vanilla supervised algorithm. I just wanted to ask how rigorous were you like in comparing these two methods? Like what kind of for vanilla setting, what did you do exactly? Could you like say some stuff?
Yeah, yeah. So over here you see that we kept the neural network architecture same. So it's like the lead module. So in case of supervised contrastive one, we are training separately. So this is the lead module we are training separately, and this particular MLPNN is basically trained up subsequent to this particular frozen lead module. The embeddings have been extracted from this frozen lead module. However, in case of vanilla supervised setting, as our aim is basically to classify the to label match the signals given an end-to-end fashion. So what we have done is basically we have taken the lead module, then we in the same go we have considered this particular MLPNN structures as well. So that is a full network in case of supervised learning. And then we have trained with the same sort of setup. For example, we have taken the batch size and other all the other hyper parameters have been tuned simultaneously such that we can get the maximum output in case of supervised learning. So we had used several batch sizes, several epochs we have employed, then number of what we call the learning rate and all the parameters we have tweaked. And we saw that several with even with the several changes in the hyperparameters as well, we are not able to overcome that overfitting part over here. However, with the base value of learning rate and all the hyperparameters that we had started with in case of uh, vanilla supervised setting, we had used those values for training the lead module and the subsequent downstream classification task. So over there, we saw that with the same value of the hyperparameters, we are able to achieve this sort of performance in case of SCL.
Okay, so the vanilla method and this lead method both have the same number of parameters, right?
Yeah.
For the
Both
method.
have same number. Yeah, both have same number of parameters. It is just different in terms of training process. In case of this one, we are training it separately. In case of vanilla one, we are constructing this whole computational architecture at the same go, and we are training it on the same flight.
Okay, and this in the lead method, you actually like so there is this is some kind of pre-training, right? Then you like fine
Yeah.
tune it on the.
Yes, yes,
Okay, I
yes. So
see.
this is sort of a pre-training, such that we
So
get good representations. Yes.
okay, I see. Hmm. So it is possible that you have like you could, if you take some supervised like pre-trained supervised network which is trained on similar data, and then you fine tune your supervised network on that one.
Yes.
You take that vanilla
Yes.
network.
Yes. Yes. Yes.
It is possible
So
that you can match the performance.
yeah. We also have done that also. So if I just show you the paper once. Uh, I think we have done that experiment as well. Let me just see. Yeah. So as you have already told that we can use some sort of a we can take some sort of neural network architecture which is basically trained previously on similar type of data, and then we can do transfer learning or fine tuning mechanism. So what we did is basically we took existing architectures like ResNet architecture, MobileNet, ShuffleNet V2, and we did the transfer learning mechanism based fine tuning examples of them. So there we saw that for this particular lightweight CNN, so these weights were given in GitHub in their repository. So we saw that with this particular CNN architecture, we got the highest one. But AsthmaSCELNet, it basically performs well than this other one. So another prospect of these sort of neural network architectures like ResNet, MobileNet, ShuffleNet, etc., is basically you see that these models were basically trained on ImageNet dataset, and we tried to fine tune that ImageNet based what you call weights. However, this lightweight CNN, what they did is basically this paper is also for lung sound classification. So this lightweight CNN was trained from scratch. So when we used that particular lightweight CNN and we used their weights to do a pre-training based on our own data, we saw that it performed well. However, as these model like ResNet 50, MobileNet, ShuffleNet, as these have been trained on ImageNet data, and as because we are training on the melspectrogram data, so the melspectrogram data looks something totally different than a simple cat, dog, some other images, realistic images. So they were not able to perform much better in case of the melspectrogram based fine tuning. However,
Yeah, okay.
there are some other networks as well you can venture out. For example, these are called PANN, pre-trained audio neural network. So these have been came up around 2020 or something. There are several architectures like VGG-ish. So that is trained on audio set dataset. So audio set is a Google library of audio signals. And there is another net called YAMNet, yet another mobile network. So they have been trained on a big corpus of audio signals using the melspectrogram, and you can use those for fine tuning the your own particular audio classification task as well. So for this particular paper, we did not consider that one because we came across those models later than this particular paper. So in some of our current work, we have considered those models as well.
Yeah, thank you. I mean, 98% already looks good, so I don't think there's much to improve there. Yeah, thank you.
Okay, so if there are any other questions, people can ask. If not, okay, so there are no other questions. So I would like to thank Orko once again for the really good presentation. And we'll be closing the meeting now, and we'll meet again next week. Thank you, Orko.
Yeah, thank you. So I will be sharing the slides with you, right?